Alright, so we're doing some examples from 4.3 using the first and second derivative tests for local extrema. And just so we can remember what's happening here, the first derivative test said that if f prime changes, well, first off, you find x equals c is your critical point. If f prime changes from plus to minus at x equals c, right, that means we have something like that, and that is the local max. And then if f prime changes from minus to plus, you have something like that, right? So that would give you a local min. And then the second derivative test, and again, this is a test for local extrema. If x equals c is your critical point, and f double prime of c is positive, then that means concave up, right? And so that means local min. And if f double prime is negative, that means you have a sad face, local max, concave down. Okay, then if f double prime of c is equal to 0, test fails. It's inconclusive. You can't tell. And so that means you have to go to the first derivative test, hopefully, to see what's happening. Okay, and so we were just working. Let's try an example. Which one shall we try? Here's f of x equals x to the 2/3 power times 6 minus x to the 1/3 power. And we want to find the local extrema. And we will go ahead and actually do even more. We're going to find where f is increasing, decreasing, concave up, concave down. So we're going to do the whole ball of wax here. And so now this function, it's not hard to differentiate, but it is hard to simplify. And so I'm going to give you the derivative simplified to be 4 minus x divided by x to the 1/3, 6 minus x to the 2/3, and f double prime of x is equal to minus 8 over x to the 4/3 times 6 minus x to the 5/3. We could probably spend the next 10 minutes doing the algebra for these two derivatives. So you might try it if you're if you want some practice with algebra. You might see if you can get your answers in these two forms. But I don't want to spend a lot of time on the algebra, so if this were like an exam, I may even give you the derivatives as well, so you don't have to try to simplify them. Okay, so how do we start? Well, I want to find where the first derivative is positive or negative. And so what I'm going to do then is I'm going to build a table, a sign chart for the first derivative. And so I'm going to list the factors over here: 4 minus x, x to the 1/3, and 6 minus x to the 2/3. And then under here, we'll write down our where each of these is equal to 0. And so 4 minus x is 0 at x equals 4. X to the 1/3 is 0 at 0. And 6 minus x is 0 at 6. And so therefore our number line has been broken into 4 pieces. And now we put in sample points in each region. And so 4 minus x, let's see, if I put in like negative 1, that would be 4 minus minus 1. So that'd be positive. Positive. And then it changes sign at x equals 4. And then it's going to stay changed after that. The cube root of x, that's only one sec. I think. Yep, so cube root is negative when x is negative, positive when it's positive. And then 6 minus x to the 2/3 power. Now this is the cube root squared. This is the when you see the 2/3. That's the cube root squared, so anything squared is positive, so it's actually positive all the way through. Okay, and so therefore now we can note if x is less than 0, my function is decreasing, increasing, decreasing, decreasing. Good. And so therefore, from the first derivative test, we're going from decreasing to increasing. 0 is a critical point, right? And so that's going to be local min. And then we also have x equals 4 is a critical point. And so that's going to be a local max because we're going from increasing to decreasing. Anything happen at 6? We're going from decreasing to decreasing. Nothing's happening at 6. We're just decreasing, so neither. Good. All right. Can we do the same thing now with the second derivative? Well, we don't have the extra numerator term, so we just have the denominator. X to the 4/3, so we can include our x to the 4/3 and 6 minus x to the 5/3, right? So then we just have 0 and 6. And then x to the 4/3, what's that? That's the cube root to the 4th power, and so that's actually going to be positive everywhere. And then 6 minus x to the 5/3, let's see, so if x is negative, 6 minus x is positive, so that's going to be positive. And then between 0 and 6, for example, x equals 1, that's still positive. And then if x is bigger than 6, like 7, that would be minus 1 to the 5/3 power. That'll be negative. Good. So you see here that our function, actually we have a negative 8 up here, so we could even include the minus 8 if we wanted to, just to remind ourselves that that is a factor when we're computing our derivative, but it doesn't really change, right? But what is important is we want to be able to take into account all the factors when we're deciding if the whole second derivative is positive or negative. And so in this region we have concave down, concave down, and concave up. Good, so we have a change in concavity at x equals 6. Remember what we called that? Inflection point. Good. And now if you look over here to the first derivative, to these 2 points, 0 and 4, what happens at x equals 0? Can you use the second derivative test? Well, the second derivative does not exist at 0, so therefore you cannot use the second derivative test at x equals 0. How about at x equals 4? At x equals 4, our function is going to be concave down. So f double prime of 4 is negative, so therefore we have a local, negative means down like that, max. Okay, good. And so that's all the information we have here. We have quite a bit. Lots of information about the function f. Good, okay. We could probably sketch this function, but I think that's probably enough information from that one. And I'll pause the video here and we will take a look at a graphical example. Okay, so here's the graph of f prime of x. So this is tricky, right? Because this is not a graph of f of x. This is a graph of its derivative. So where are the critical points? Well, the critical points are where f prime is equal to 0 or does not exist. And so from this graph, where are those points? Draw them in red. X equals 1, x equals 3, and then really x equals 4 should be included, right? Because that's also a point where the derivative does not exist. Good. All right. So where does f increase? F increases where f prime is greater than 0, right? And so could you see those regions? Here I'll draw those in green. From 0 to 1, and then from 3 to 4, and then from 5 on. So we have 3 regions. X is between 0 and 1, X is between 3 and 4, and then X is bigger than 5. Notice I'm not including those points. Oops, did I forget 5 in my computation? I did. Let's see, where's my critical points? I guess I didn't actually write them down, huh? What am I doing? X equals 1, 3, 4, 5. Okay. Let's see. Now, so f is going to be decreasing in the other intervals. So f is decreasing here, and f is decreasing here. Okay. And so let's do the concavity now. Where's f concave up, concave down? It looks like if I use the, let's see, I need a different color. How about multicolor blue? In this region right here, it looks like purple. Oh no! Sorry about that, my curve disappeared there for a minute. Okay, so it looks like from 0 to 1, the curve is concave down. And then from 1 to 3, it looks like we're concave up. Right, and then from 3 to 4, it looks like we're concave down. And then from 4 to 5, we're concave up. And then from 5 on, we're also concave up. Good. Oh, wait a second. Did we do that right? I don't think we did. Did you do that? Does everybody see what the error is? This is not the graph of f. This is the graph of f prime. So using the graph of f prime, how do I know if f is concave up? F is concave up if f double prime is positive, right? And so, okay, so how am I going to tell that from the graph of f prime? Well, maybe we'll do a side note here, If g of x is increasing, then we know g prime is greater than 0. And if g of x is decreasing, g prime is less than 0. So now, what happens if we replace g by f double prime? Then what we'll say is f double prime is positive if f prime is increasing, and f double prime is negative if f prime is decreasing. Good. And so that'll be straightforward to show here. Let's see. So where is my function, where is my first derivative increasing? My first derivative is increasing here and here. Right? And where is it decreasing? I'll use a different color. I'm using too many colors here, I guess. It's going to be decreasing here, right? Good. And so, yeah, that's it. You can kind of see here what's happening with our local maxes and mins. Do we have any local maxes and mins? Well, we can use the first derivative test, right? So here at x equals 1, we're going from positive to negative, so the original graph looks like that. So that's going to be local max. And here, we're going from negative to positive, so it looks like that, local min. And what's happening at 4 is we're going from positive to negative, right? And so if it exists, if our function exists there, positive to negative would look like that, so we have a local max. Good. All right, we went way over time on this one. We'll try another example, though, in another video.